Hello students, I am Dr. Tanmoy Biswas. I welcome you all in my channel TanmoyChem. Today's topic of discussion is one MCQ and the question is in front of you. Which of the molecule can't produce CO2 from sodium bicarbonate solution? I suggest everyone please pause the video, try by yourself, and whatever answer you get please write in the comment box along with few words as explanation. I believe you have tried, so let's start. Now we have studied previously that organic compound react with sodium bicarbonate solution and produces carbon dioxide gas. Organic compound, or technically if I say carboxylic acid, this reaction is actually a detection test of carboxylic acid where along with CO2 sodium salt of carboxylic acid is produced. For example, if you take acetic acid, product will be sodium acetate and carbon dioxide. This carbon dioxide bubble or effervescence proves the presence of carboxyl group on organic acid. This is the common thing, but today's question is not that. Today's question is that if you look at, this is a sulfonic acid, this is a dinitrophenol, and if you look at, this is actually a 2OH group, actually it's a squaric acid. So question is, which of the molecule can't produce CO2 from bicarbonate solution, or all? Fourth option is all produces CO2 gas from this bicarbonate solution. So it's a pretty interesting molecule. By the way, this question is about the acidity, because this property or this chemical reaction is displayed because of the acidic behavior of this carboxylic acid. Now for that purpose we need to look at the acidity of all these three molecules, and the thumb rule is that if you want to compare about acidity, you need to focus on the stability of conjugate base. Means higher the stability of conjugate base, higher is the acidity. So what is conjugate base? If you remove the proton from this molecule, whatever negatively charged species remaining, that is called as conjugate base. Now if this conjugate base is more stable, acid will be stronger. Look at the first one, it is called the benzene sulfonic acid. In this case, the conjugate base is stabilized, could be stabilized by two ways. By the way, I am not drawing everything. So here you can expect this is SO minus double bond O, again double bond O. And if you want to draw the second canonical form, it will be similar. I am not drawing same. So by the way, two canonical forms are possible and both are same, and this is technically called as equivalent canonical forms. So what does this mean by equivalent canonical forms? Means electron density. See, negative charge means excess of electron. This extra electron is delocalized very strongly, properly. So if it is delocalized, means it is stabilized. So if it is stabilized, so acidity is higher. And these benzene sulfonic acid is, student, strong acid. Technically if I say, it is a very strong acid. You can consider this is the organic version of sulfuric acid. It is similar, stronger. I shall give pK after some time. Now if you look at the next one, it is a 2,4-dinitrophenol. So the 2,4-dinitrophenol could also be stabilized by the resonance with this NO2 group. By the way, I am all showing only one canonical form. I suggest you please draw rest of canonical forms by yourself. So how it is stabilized? So it comes here, it comes there. I am showing only one canonical form where I want to show how the NO2 group is helping to stabilize the negative charge. So now it will come here, it will open up. So what should be the canonical form look like? So it should look like this. This is the double bond O. Look at the negative charge on oxygen actually delocalized over the nitrogen. Oxygen means NO2 group. By the way, please do not get confused why nitrogen carrying positive charge, because remember nitrogen cannot exceed its tetravalency. So that's why it's carrying positive charge and neighboring one oxygen carrying negative charge. That's a different thing. Now similar kind of stabilization possible for this ortho one also. I'm not drawing. Many canonical form possible. So which indicates that okay, the conjugate base from this 2,4-dinitrophenol is significantly stabilized. So this is also significantly acidic. And third compound is very interesting. Its name is squaric acid. Now if you remove any one of the proton, by the way, only these two proton available, no more proton available in this molecule. So any one of them, because both are same. So if you remove its O minus, now question how it is stabilized. So that thing, if you want to understand, you need to draw a canonical form. It will come here, it will go A2. So you can see that the negative charge is delocalized very much efficiently, and in this case student, you may consider this is actually a equivalent canonical form. So by the way, this parent one and this one stable, so you can try to draw others also, so I'll not go that much in details now. But here these two canonical forms are same. So what does it mean? The negative charge is delocalized efficiently, so it is stabilized. So that's why this squaric acid is also a significantly stronger acid. Now let's look at their pK, acidity versus pK. So this sulfonic acid's pK is minus 2.8. So you may understand how much stronger acid it is. Its acidity is like inorganic acids. Now if you look at 2,4-dinitrophenol 3.96, so nearly 4, significantly strong acid. And the squaric acid pK 1.5, very strong compared to structure, you may think like that. And if I say acetic acid, which commonly gives these bicarbonate taste, its pK is 4.74. So from this discussion you understood one thing, I guess, that compared to acetic acid, this sulfonic acid, benzene sulfonic acid, 2,4-dinitrophenol or squaric acid, stronger acid, so all will give positive taste for sodium bicarbonate. So this message I want to give. Now here you may have little doubt about acidity of squaric acid. So look at here. So there could be resonance. Resonance means you can expect that okay, this proton can go from there to there, or there to there, so they can exchange and they can form this canonical form. And by the way, after removal of this proton, it is again it can remove the second proton also, resulting in a dianion. So it is a diacid. Okay, it's a diacid. And look at their pK 1 and 2 are 1.5, 3.5 means significantly stronger acid. Now why this unique property is observed in this molecule? Now that thing you can answer from this structure. Look at, so there is a canonical form they have drawn, that okay, so it could be taken there. By the way, you may consider this is actually a canonical form, not say equilibrium, and it can come there also. So negative charge on two oxygen, positive charge here. By the way, I'm talking this is neutral. Okay, same thing is possible for this anionic also, I shall come. Now here two positive charge and one pi bond. So look at Huckel rule for aromaticity, 4n plus 2 number of pi electron, and if n is equal to 0, it means 2 pi electron. So look at these are the 2 pi electron. Positive charge means vacant p orbital but no electron, vacant p orbital, no electron, and they are in conjugation. So recall the rule, cyclic planar conjugated, 4n plus 2 number of pi electron. So this ring is student actually aromatic, and you can write it is cyclobutadienyl cation. So that thing is this squaric acid's 4-member ring. So this is actually the uniqueness. So you can understand this part is stable because it is aromatic. So that's why it shows higher stability. Now if you look at this dianion, how can you draw it? By the way, student, practice drawing in home, it is essential for learning. So all 4 oxygens are in negative charge. Now you may think, sir, 4 negative charge really stabilized? Answer is yes, they are stabilized. Why? Because there is a positive charge inside and outside 4 negative charge. So close proximity of opposite charge stabilizes this. So that is the reason why the pKa values are significantly lower. You can consider it is relatively stronger acidic, okay, compared to if I say acetic acid. So this is the reason behind the acidity of squaric acid. So let's go back to our question. Which of the molecule can't produce CO2 from sodium bicarbonate solution? Actually all can produce. So option D will be the right answer. All produces CO2 gas. Now if this question appears in your exam, how can you get the right answer less than 30 seconds? I would suggest student, remember these all 3 options are very unique. That is the reason I have selected this. So you should remember this option. Compared to carboxylic acid like acetic acid, squaric acid, nitrophenol, they are stronger acid. Even if you look at trinitrophenol, 2,4,6 trinitrophenol picric acid, it is even stronger acid. Okay, so that can also produce carbon dioxide from sodium bicarbonate solution. So this is the overall discussion. I believe this video may be useful. I thank everyone for watching this video. If you really enjoy the content, please like, share and subscribe. And if you have any doubt regarding the logo of my channel swastika, I request you to read this part. Your doubt will be clear. See you in my next video. Bye bye.